Okay, welcome back, ladies and gentlemen. This is Kieno Thomas here, and we are continuing our series on meteorology for professional pilots. I got an email, and in our last video, we talked about lake effects and how water or large bodies of water can have an effect on air masses and the kinds of weather that could be produced in certain situations. Like here we have a cold air over a warmer lake producing showers, and then we have warm air over a colder lake producing fog. So what I decided to do was to just revisit that a little bit. Okay, here's a sectional, and this is and the sectional is just a map. This is the Finger Lakes area in upstate New York, south of Lake Ontario. Rochester and Syracuse and all that stuff is to the north of here. But this represents a warm air mass, okay, overlying the land. We're looking top down. So this is an air mass. And here we have our wind direction. So we can see that the wind is coming out of the west. Again, whenever I talk about a map, north is up top, east is to the right, west is to the left, and south is to the bottom. And for all our navigators and pilots down here, we could see a VOR, a very high frequency omnidirectional range navigation beacon, which always points to magnetic north. So the 0 is magnetic north. So that would be another indication. But anybody looking at my videos, whenever I lay out a map, north, south, east, west. Alright, so we have our wind direction, and it is coming out of the west. Winds are coming out of the west. And we have our warm air mass, sorry about that, our warm air mass indicated by the red, warm, hot, or warmer. I mean, this could be wintertime, but this air mass is warmer. Alright, so this lake could be, I don't know, 32 degrees. This warm air could be 40 degrees. It's still cold, but it's warmer. So we have our warm body of water, warm air mass. It starts here, and then it goes over this large lake, which is one of the Finger Lakes. When it comes over top of the Finger Lakes, we have colder water, and there's still going to be some evaporation going on. And what's going to happen is this warmer air mass is going to be saturated. And as a result, what we're going to get is fog. I just wanted to show our air mass overlying the area. I'll reduce it, but we can see fog. And fog is a cloud, but it's just a cloud that comes down to the ground. So we still have our clouds up there, but we have a fog layer on the bottom. Our next example is a cool air mass over a warmer body of water. In that situation, when the air mass starts here, wind direction pushes the air mass, comes over, and moisture is added to the air mass via the warm air rising, warmer air. And as a result, what we get rain. Rain clouds, rain, not so much fog, but we'll get low ceilings or lower level clouds, not to the extent of fog, but when this cold air mass picks up moisture from this lake, this body of water, we're going to get rain. This is the windward side of the lake in particular, and this would be the leeward side. So the weather happens on the leeward side. just covering my talking points. Now we're going to jump into air masses. Since we kind of dug into air masses, we have our warmer air mass here. We have our cooler or colder air mass here, represented in blue, and that segues into unstable air masses and stable air masses, or we say stable and unstable air masses. And this is just a picture, ladies. I don't want you to get all bent out of shape. It's just that the lady to the left, she just happens to be mad, so I don't want to get into any gender thing. But she's heated, she's hot, she's unstable, and he's just sitting there just calm and cool and collected. So this is how we like to think of our unstable and stable air masses. So what is a stable air mass? A stable air mass is an air mass that resists upward or downward displacement. So it resists upward movement and downward movement. An unstable mass, conversely, it allows upward and downward movement, and it even allows the disturbance of the air mass to grow into a vertical or convective current. So it's really, really important that we as pilots understand stable and unstable air. This is pretty much a stable day, not a whole heck of a lot going on, where this would be an unstable day. And if you looked at our previous video, this is a microburst. Thunderstorm activity happens when we get microbursts, so the thunderstorm activity causes the microburst. Very, very unstable air, because this air mass or this atmosphere or part of the atmosphere is not resisting vertical movement. This atmosphere, or this picture of the atmosphere, is pretty much resisting vertical movement. Very, very stable air. And we could look at it as experienced pilots, but the unexperienced pilots may not know, so we'll dig in. So make sure I hit all my talking points. In this section, we're going to discuss fundamental changes in upward and downward moving air. This guy, unstable air. And then we'll talk about how stable and unstable air results or relates to clouds, weather, and flying. So anytime air moves upward, it expands because of decreasing atmospheric pressure. We'll go back to our little guy in our little Eskimo, I call him. And if you looked at or checked out our previous videos, you saw this. You've seen this clip before. Down at the bottom, we have high pressure. Up at the higher altitudes, we have lower atmospheric pressure. So, as this air moves upwards, it's going to expand because of the decreasing atmospheric pressure. Conversely, downward moving air is going to be compressed because of the increasing atmospheric pressure. So up, decreasing or lower atmospheric pressure, coming back down, increasing or higher atmospheric pressure. But pressure and volume, as the pressure and volume changes, so does the temperature. Now this is a pretty cool thing that I thought it was pretty cool. I always say stuff is pretty cool, and guys tell me, oh, that wasn't that cool. And that's fine. But the objective here is for you to understand. Down here at the bottom, like our little man at the bottom of the mountain, or our Eskimo at the bottom of the mountain, was in an area of higher atmospheric pressure. So if we take a balloon and we let it go, some things are going to happen. The actual air inside this balloon, the air molecules are going to expand. Back to our previous clip about lower atmospheric pressure. Alright, we said anytime air moves upward, it expands because of decreasing atmospheric pressure. Back to our balloon. So as this balloon gets caught in the wind and it gets to a higher altitude and a higher altitude, the balloon is going to get bigger. So what's happening inside? The volume is changing. The air molecules are spreading apart. It's less atmospheric pressure exerting itself on the balloon. So the balloon is like, wow, I could be free, man. My molecules can spread apart. And there's a temperature change also, and we'll get to that in a minute. But right now, I want you to understand that as we increase in altitude, the parcel of air inside the balloon, the volume of it is changing. So it needs more room, so the balloon actually expands. All right. So oftentimes we're gonna use the term expansional or adiabatic cooling, because, like we said in the previous clip, temperature is also going to change. So it's kind of like the lapse rate. As we go up, what happens? I'll pause for a second. As we climb, we're going to lose a couple degrees per 1,000 feet, and that's called the lapse rate. So that's going to bring us into talking about lapse rate. So that's one thing, temperature change. And then we're going to talk about saturated versus non or unsaturated air. So if we look at this air in this picture, there's a certain amount of moisture in this air. Okay, we go back to our condensation nuclei in the previous video, and how water vapor or water droplets attach to it. All right, and we talked about relative humidity. When the relative humidity is high, or 100%, the air is said to be saturated. All right, when the temperature and the dew point are equal, then we get saturation, total saturation. And another thing is evaporation ceases. So there cannot be any evaporation if the relative humidity is 100%. So for our purposes, unsaturated air will be any time that the air is less than 100% relative humidity. So at 80, 70, 60, 50, 40, 30, 20, 10% of a relative humidity, we would call that unsaturated air. All right. Now back to our dry adiabatic lapse rate of temperature change. All right. This is independent of the actual air mass. So as this balloon increases, there's going to be a dry adiabatic lapse rate, which is 3 degrees per 1,000 feet. If I'm not mistaken. Yeah, next clip. Unsaturated air moving upward and downward cools and warms at about 3 degrees per 1,000 feet per 1,000 feet in Celsius, and 5.4 degrees per 1,000 feet Fahrenheit. So this is our dry adiabatic rate of temperature change. And again, it's independent of the air, the outside air. Make sure I hit all my talking points. So one good example is this is a good example of adiabatic warming. Winds blowing from the left side of the screen. This is the Rocky Mountains, and the cool air is forced upward, comes over the top of the peaks, and the Rocky Mountain peaks range about 14,000 feet. And then it flows downward. So, like we said, cool air goes up, expands, and the temperature drops. And then as it comes back down, it's going to descend, and it's going to get warmer. The air molecules are going to get closer. A cool example of the Rocky Mountains, again, we have another sectional. This is the Rocky Mountain region out here. And typically a lot of times what happens is air flows from west to east. It flows from this direction. And here we can see like some of these peaks are at 14,000 feet. Down here, Denver International Airport, the altitude above sea level is about 5,400 feet. So we have peaks at 14,000 feet And then that wind blows down. This is why I added this picture, so you can kind of get a visual representation, because it's really not as notable unless you understand the color contours or color contouring when these maps are designed. This darker brown represents, or tannish darker brown represents, higher altitudes. All right, and then in each one of these grids, we have something called a maximum elevation figure. So maximum elevation in this here grid, denoted by these tick marks, this will be a grid, is 14,600 feet. We get down here, or in the Denver area, and the highest elevation is about 6,800 feet in that particular grid. So that is a very steep drop. So if wind is kind of blowing over the peaks and then coming down, we have a very steep drop. And then I also added a picture to just kind of remind you why I brought this sectional up. So we can expect certain types of weather, winds, drying effect, warm winds in the summertime when this Chinook. So this is an example of where Chinook winds where it happens. The wind comes over, atmospheric pressure is decreased, we get cooling and expansion, and then it gets pushed over the peak of the mountain and the winds just come sweeping down. Atmospheric pressure increases, the air compresses, and it warms. And then this airport area gets a whole bunch of westerly winds. So we would probably want to be landing in a westerly direction on this runway or that runway. The book goes into condensation, and I'll bring it back. Okay. It comes back to our previous video when we talked about dew point. All right. As the condensation occurs when the saturated air. So if we have air saturated, 100% relative humidity being pushed up, and we'll talk about ways that it can be pushed up. What happens in the morning when the air is cooled? The water vapor goes from a gaseous state to a liquid state. And I'm still calling that deposition, if we go back to our chart in the previous video, because deposition occurs when we go from a gas directly to a liquid state. Or my bad, not deposition. Condensation, I'm sorry. Had a brain fart there. Alright, deposition is in the form of ice crystals, frost. If it goes from gas to frost, that would be deposition. My apologies. Now, so this saturated air moving upward is very, very similar. Water vapor just starts to come out, or not water vapor, but moisture starts to come out in the physical form, which is liquid. And that gives you an idea of how storms are started, but we'll dig into that later. So, as pressure and volume change, temperature also changes. We come back, and we can see our expansion, and we can see our warming. So as the air goes up, we're going to get cooling and expansion, and as it goes down, it's going to compress and warm. I know I'm beating a dead horse because I really, really, really want you to get this and understand this for later. So when I touch on topics, you're not totally lost. Alright, so if we force a sample of air, this is our sample of air, up into the atmosphere, we have to consider two possibilities. This parcel of air is going to become colder than its surrounding air. I made this a dark blue to say, hey, it's chillier than this air. The second situation is, even though it may become cooler, it could still be warmer than the surrounding air. And so if it's cooler than the surrounding air, it's going to sink. If it's still warmer than the descending air, it's going to keep moving upward. Which brings us back to our stable and unstable air masses. Here's an example of some Navy guys, or Navy people, because they're not all guys, some Navy people, and This is also a book reference, not this particular thing I set up. I set this up on my own. The water temperature in the picture is 31 degrees. The ambient air, or the air in the balloon, is 31 degrees. Alright, so at sea level, which is what these people are at, the temperature is 31 degrees. So if we consider a dry adiabatic lapse rate, we should lose 3 degrees per 1,000 feet. We're going to release this balloon and we're going to just collect data from sea level to 5,000 feet. So if a dry adiabatic lapse rate truly exists, then what's going to happen is at sea level we're going to be 31 degrees. 3 degrees we're going to lose per 1,000 feet. When the balloon gets to 1,000, we're going to be at 28. When the balloon gets to 2,000, we're going to be at 25. 3,000, 22. 4,000, 19 degrees. And then 5,000 degrees, we should have 16 degrees Celsius. Okay. So, just to give you an example of a couple things that could happen. All right. We get this balloon to 5,000 feet, and the outside air temperature is 16 degrees. Well, the internal temperature inside the balloon, or the air inside the balloon, is 16 degrees. So, if the temperature is 16 degrees and outside air temperature is 13 degrees, air outside the balloon, and that's what OAT means, not Quaker Oats, outside air temperature. It's just an abbreviation. So, 16 degrees Celsius, and outside is 13 degrees. So the inside air is warmer. What's going to happen in this case is the balloon is going to keep rising. Alright, because it's warmer. In the second situation, we still release the balloon, gets to 5,000 feet. At 5,000 feet specifically, the outside air temperature is 18 degrees. The internal temperature of that balloon cooling at a dry adiabatic lapse rate is 16 degrees. So outside air temperature is 18, internal temperature of the balloon is 16. The balloon is going to descend. And in our third situation, and this should be a 6, we'll correct that, backspace, 6, alright. So in our third situation, the balloon is released, it gets to 5,000 feet, the internal balloon temperature is 16 degrees Celsius, the outside air temperature is 16 degrees. This balloon is not going to rise, it's not going to ascend or descend. Alright, it's going to remain at rest because this is neutrally stable. Okay, so this is to give you an idea of stable and unstable air. Alright. Stability runs the gamut from absolutely stable to absolutely unstable. And here's some examples. We have some unstable air mass, winds blowing like crazy. Here we have another situation where the air is unstable. Otherwise, we would not be getting these scary clouds. This cloud is called, it's a cumulonimbus cloud, but it's a cloud with vertical development. You can see these clouds, they're puffy and stuff like that, but there's no vertical development. In this case, we can see something is going on. And this is a thunderstorm cloud. We know this because we could see the anvil at the top of the region. So there's a delicate balance. And really, in a lot of cases, all you need is some temperature to throw it off. Alright? So a change in ambient temperature, lapse rate of an air mass can tip this balance. Alright? We can adjust temperatures by, back to our word, terrestrial radiation. Alright? Solar radiation. So we can warm an air mass from the bottom, or we could cool it. And as we talked about, our fog, a warm air mass over a cooler surface. When we got warm over warmer sea surface, we don't get any situation. But when that warm air mass moves over a colder sea surface, we start getting fog. And so it just allows for the water vapor to become visible. Alright? So we're going to talk about that a lot. Cools to its dew point, and then we got low visibility fog. Alright. So the land mass or water area cools or heats from below, and that dictates or helps or not, or helps or does not help stability of an air mass. So when air is cooling, it first becomes saturated, condensation or sublimation. Condensation is basically gas to water, or sublimation is that ice crystal type situation, because clouds are not always water. Sometimes they're ice crystals when we get to the higher altitudes. Alright, so whether the air is stable or unstable within a particular cloud determines, well, whether the air mass is stable or unstable. It determines on, we could see it by cloud structure. Alright, so back to our stable air situation. Stable air resists convection, or upward-downward movement. Stable air is like, look, man, you can't move me. I'm not playing. I'm going to sit still. So what happens is the type of clouds that form in stable air are strata, which is sheet-like. All right, or carpet. I like carpet even better. It looks like somebody laid a carpet in the sky. Or stratiform clouds. So within a stable layer of air, we get stratiform clouds. In our Rocky Mountain situation, we can get stable or unstable clouds, but we get that cooling, which is stabilizing that air mass, and if it remains stable, we'll get a stratiform cloud. So the layer must remain stable after the condensation occurs. After the cooling occurs and the water vapor comes out, it has to remain stable, and then we have cloud indicators. This is called a lenticular cloud. All right, it looks like the shape of a lens. So we brought you back here to say, okay, we got air being forced up this upslope to the top of the peak, and then we'll see some results by clouds. All right, so if I'm flying in this area, I know that air is flowing upslope to make this cloud. All right, it's very, very important that we understand that the clouds are the signposts. The clouds are telling you, hey, this is what's going on. So we can look and see as we get more and more experience with meteorology. Here, I see unstable air. All right, we don't have those carpet-like clouds. We got our cumulus clouds, man. They're just kind of all over the place. So this would indicate to me, at this flight level, we're probably going to get kicked around a little bit. So at this point, this is pretty much all I want to touch on, and we're running close to the half hour. I'm trying to keep these things close to a half an hour, because this is not the most exciting material in meteorology or aviation. This is going to segue into clouds, cloud identification, development, things of that nature. So again, I hope you guys are enjoying this series. If something was not clear 100%, just email me or leave a comment in the comment box. But I thank you guys for watching. This is Kieno Thomas with Meteorology for Professional Pilots. Thank you.